Okay, let's go back and review a little bit about what we talked about last class. So where are we on the list? Everybody okay with electrical circuit, conductor, insulator? Now we know the natural metals that are best conductors, right? Everybody okay there? We know the two most often used electrical conductors. Everybody okay there? What's voltage, current, resistance, and power? Are we okay there? And so we're fixing to get into the differences between AC and DC. Oh, I'm sorry. We did talk about a short, right? I think where we left off was when we talked about open. Yeah. And of course, you just live with it when people start talking about they've got a short, right? Odds are most of the time they say they got a short, they actually got an open. So shorts are bad. Opens are not good, but shorts usually cause things to cascade or damage or fires and stuff like that. Opens will not cause a fire. Huh? Oh yeah, they're all about that. And they don't understand that. It's okay, you know. Just as long as you know the difference. So in here, if you call it a short and it's open, that would be different than your buddy calling it a short and an open. We looked at parallel circuits, just a basic look at series circuits, a basic look at parallel circuits, and then a basic look at series parallel circuits. Electronic circuits are usually series parallel, and then power circuits are usually parallel, right? Look at some symbols of different devices that conductors actually attach to. So these are the some of the devices that the conductor attaches to, right? And of course, in here we're looking at two things. We're looking at termination and splicing. Y'all understand the difference between those now? What's splicing? Huh? No, what is splicing? That's when we connect two wires together. That's the way we connect, physically connect two wires together, two conductors together. And then what's termination? Yeah, every conductor eventually comes to an end, right? And the art of bringing that conductor to an end is what we refer to as termination. And of course, normally what we're looking at is getting the current from the source to a load. And conductors is responsible for that. We looked at some prints for house wiring. Talked about voltage, amperes, and resistance and reactance. Reactance and resistance are a little different, and we're going in communication cables, not in power cables. And that's not really true. Engineers have to worry about reactance even in power cables. But it's extremely important to understand reactance in communication cables. So we have two types of opposition in a circuit and even in a conductor. We have what we refer to as resistance, which y'all are all familiar with resistance. Y'all all had intro, y'all all had DC. So you understand R. But what we need to do is understand in cabling, we need to understand, in AC, we need to understand something called reactance. Now, all opposition to a flow of current in a circuit use the unit called ohms. So this is true Ohm's law right there. So you learned that V is equal to I times R. It's actually V is equal to I times ohms. Because in a circuit, you have different types of opposition in the circuit. And we'll talk about that before long. And we went through some problems. this is the big difference, and when we get in to learn a little bit about AC, is that in R has nothing to do with something called frequency. But the problem with reactance is reactance only applies to a circuit that has AC, alternating current. DC, there's no such thing as reactance in a DC circuit. But AC, we're very concerned about what we call reactance, and because it does what? Yeah, it varies with frequency. So voltage drop. Everybody okay with voltage drop? We looked at an ideal circuit, and then we looked at a real circuit in DC. So everything that we deal with has an R component, right? You understand that? And if we push current through R, what do we get? We get a voltage drop. So it means all your conductors are going to drop a small amount of voltage, right? Now, if we choose the right size for the right length, this voltage drop is so small, it's really negligible. But when you deal with people that's got to deal with conductors that are miles instead of inches, then there's no way in the world we're going to get rid of R, right? You understand? So transmission lines, we're really concerned with the R of the line. And even us, I mean, so if I'm running a light that's 400 meters or away from my house, then I'm going to be concerned with the R of the wire, right? And of course, I could use a big wire, but what's the problem with use? What are we shooting for when we size these conductors? Well, we'll never get that. What are we shooting for? If I'm an electrician, what am I trying to do? I'm trying to use the smallest conductor I possibly can use to support that load. And why is that? Yeah, because of the cost. I mean, I've seen some pipes running under interstates. You know, they'll handle just about every amp there is. But I'm not going to run that through my backyard. That's okay. I never make mistakes. I'm not going to go there. So that's what we're shooting for, and that's what engineers shoot for, is they shoot for the smallest possible conductor they can possibly manage to handle that current over that distance, right? Y'all understand that? We looked at the American wire gauge. Of course, some of it's cut off here on the recording, but I gave you a copy of it, right? Which is pretty interesting. And of course, the American wire gauge is usually used to be only set up in inches, but also now the American wire gauge has not only specifies in inches, but they also specify in millimeters. And then they specify the amount of ohms per 1,000 feet and also per kilometer. So now would be okay if we even use gauges overseas. We talked about work. We okay with power? So we have three formulas that we will use. And I'll give you these. This is the one you need to know. These right here we'll use a given to you. We'll use these later on when we start talking about matching opposition in a circuit. Then we did some problems, and we looked at, remember, power varies with the square of the voltage, right? You understand that? Because if we change the voltage, what do we change in a circuit? We change the current. And the current, since current and voltage are directly proportional to each other, if we half the voltage, we half the current. So that would drop the power by 1/4, right? You understand? If we raise the voltage, if we double the voltage, we double the current. So that means the power would go up by 4. So that's why voltage is really, really critical to a circuit. Shorts. We okay with shorts, overcurrent protection devices? Y'all okay with that? Looked at some examples of shorts. Of course, the purpose of the insulators are to keep that push in. So voltage is push, and what's voltage trying to? Voltage is trying to push electrons. And if you have a difference in potential, and you got a path, then voltage is going to push electrons. So what we do is we enclose that into it's just like a pipe. What's the purpose of the pipe? Well, it's to hold that water in, right? That water pressure. So here we are at open. An open allows no current to flow through the load. If no current flows, no work is performed by the load in which the open exists. An open prevents current flow through the entire circuit. Now we do deliberately create opens, thank goodness. And so all your light switches and switches that you turn things off and on are creating opens, right? True switches. We don't have true off on switches on these guys here anymore. Well, these guys we call it on and off, but we're not turning it on and off. We're switching it between on and standby. So it's very hard, even when you turn your cell phone off, it's still not really off. Y'all understand that? Because you'd have to have a switch, and we don't have a switch on our cell phone. We got a push button. So your cell phone is never actually off. You can put it into an extremely low power mode, where about the only thing it monitors is that push button. So very seldom do we turn things off anymore. So, especially on electronic devices. Fuses and circuit breakers, these create opens. Our problems, of course, is faulty splices, faulty termination, and then, of course, conductors breaking. They break every once in a while. People will put them under stress. We were redoing something on the little Mitsubishi robot last semester, and to do it, we had to take it up and take it off the line and put it on a table. Well, when the students picked it up and was moving it over, they didn't disconnect the cable. And what happened? It was a little old tiny thing. Just jerked that thing right apart. So now we had an open, right, that we had to repair. So by doing what? By splicing, right? So sometimes we accidentally put opens in by putting too much stress on the conductor. Sometimes if we don't do our splices correctly, we'll create opens. Sometimes we have terminations, we create opens. Opens, true opens are easy to find. These intermittent opens, these are what's hard to find. You know, so you're driving in your car, you run over a railroad track and your lights blink off and on. Those guys are hard to find. You see people out jerking and moving cables around. So this is an example of an open. So that would be an open. So an open, we have opens and we have open circuits. Y'all understand the difference? So a circuit breaker would create an open circuit, but an open is like me unplugging something. So we have opens and we have open circuits, right? Y'all understand that? So an open would be like you turning off a light. They don't kill everything on the whole line because the circuit itself is open. It's not open, right? You understand that? So this would be an open. This would be an open. This would be an open, and this right here would be what we call an open circuit. You understand the difference? So you go out and you turn that circuit breaker off, you're creating an open circuit. You go over there and turn that light off, you're creating an open. Right? You understand that? Everybody okay there? If I turn my radio off in my car, I'm creating an open. If I go out and disconnect my battery, I'm creating a what? An open circuit. So your circuit breakers are back in here. They'll be right off the power source. And so your circuit breakers, and I should include that symbol. So the symbol of a circuit breaker is this, and then we put a loop across here. And you don't actually touch, believe it or not. So if you see that, that is the symbol of a circuit breaker. So what we do is we put our circuit breakers right here. So or we put our fuse right there. That could be the symbol of a fuse. But in houses, we don't have very many fuses anymore in the power circuit. And you got all types of fuses in your electronic devices. So fuses are very, very popular. What's the big advantage a fuse has over a circuit breaker? Yeah, they're a lot cheaper. A lot cheaper. So most of your electronic equipment will have a fuse in it. So this meter has a fuse in it. They don't have a circuit breaker, it has a fuse. Now what's the big advantage of a circuit breaker? Yeah, it's resettable. So that's the big advantage. So you don't have to keep spare fuses around your house anymore. When I was a kid, everybody had fuse boxes. And my dad used to keep spare fuses in the house. So if a fuse blew, then he would have to go in there and do what? I'll wrap aluminum foil around it if he didn't have one. That was very dangerous. Now if I put a light switch, this is a series circuit, but if I put a switch, then the switch would be over here, right? So a circuit breaker is in series or in line with everything that you're trying to run off that. In houses we call that a branch circuit. So you have branch circuits, and if you look at your box, we'll go back at a panel box, and we'll see that every one of them has a number on it, and that controls a whole bunch of stuff, right? You understand that? And then of course now we have wall outlets that I can do what with a wall outlet. I can plug something in, or I can do what? Or I can unplug it. Okay. So this is an open circuit. This will be an open circuit. Okay. Voltage across an open. So normally to find opens and shorts, we use what we refer to as a voltmeter. And we have 3 meters that we use in electronics. Okay, what are the 3 most often used meters we use? Yeah, so primarily the big one we use is the voltmeter. And the next one we use is what we call an ohm meter. And then probably the most least used is what we call a ammeter. They leave the P out in ammeter. Of course, the voltmeter is in there to measure the difference of potential we talked about, right? Well, this measures volts. Of course, this measures resistance. And then this right here measures current. Now, the reason why we use the ammeter the least is that if you're going to measure the flow, you got to put the meter in line with the current. So if I was going to come over here and set up just a very simple circuit, and we'll put a switch on it so we can turn it off and on. So what we do with the voltmeter is we're measuring the difference in potential. So we would put the voltmeter across what we wanted to measure, and then we'd turn power on. So voltmeters are across usually with power on, right? You understand that? An ohm meter, what we do with an ohm meter is we put it across, but we have to make sure power is turned off, because we don't want to put an ohm meter that's measuring resistance into a circuit with power on it. So the ohm meter goes across, but the difference between an ohm meter and a voltmeter is the ohm meter is with what? power off. If you put an ohm meter into an active circuit, there's a high probability that you'll damage your meter. And some meters are more forgiving. Radio Shack used to sell a meter called a Micronda meter. And if you ever put that meter in a circuit on ohms with power on it, the meter was gone. It wiped it out. Didn't blow a fuse, it just wiped it out. So you got to be real careful with a meter, with an ohm meter. They're not designed to be put into circuits with power on. So what you need to do is you need to make sure, and the problem is that used to we had ohm meters, we had ammeters, and we had voltmeters. But now we have something called a digital multimeter. And one of the things you'll buy inside our program is you'll buy a digital multimeter. That's your main tool. So that's a tool that you should have. And it's abbreviated like this. Now what that is, of course, it is a meter. It is actually at least 3 meters in one. I forgot to bring up my application. Let me bring it up. See if it works. So what you have on the dial of your meter, this is what we call a manual ranging meter. And this is a multimeter. So we select the meter that focuses in. So this measures AC volts. So if I want to measure AC volts, I have to turn that dial right there. So now this is a AC voltmeter. If I move it right there, I've switched over to a DC voltmeter. Y'all understand? If I switch it right here, that is an ammeter. So these are ammeters right here. This is for AC, this is for DC. This is an ohm meter right there. So there's my 3 meters. Voltmeter across the top, ammeter right here, ohm meter right there. So before you put a meter into a circuit, you've got to make sure you're selecting the right meter. I understand that. And I'll get a auto ranging meter. I prefer a manual ranging meter. This also has a capacitor meter on it. It also has a logic probe on it. It's got a function generator in it, and it's got a guide that it's an ohm meter that allows us to check solid state devices. So to be called a multimeter, you got to have at least 2 meters inside one unit. But I've never seen one that only had 2. Mainly you have a watt meter in there, you have a voltmeter, you have an ohm meter, and you have an ammeter. And then most of your meters now add more features to buy. It's just like we call it in cars, we call it standard equipment. So that's standard equipment of a car. And then what can you do usually with a car when you buy it? Yeah, you can upgrade, add what we call options, right? And as soon as you start adding those options, what happens to the cost of the meter? It goes up. So the less options you have, the less the meter will cost. The more options you have, the more it will cost. And what you need to do is try to get the options that are used for your trade, right? Forgot where I was at. Now the problem with an ammeter, and I'm going to miss that too. Tegrity had a blank page you could pop up there anytime. Screencast-O-Matic don't. Oh, there it is. The problem with an ammeter is we got to make the current flow through the meter. So what we have to do is we open the circuit, we make sure power is turned off the circuit, Then what we literally do is we come over here and we open the circuit. Then what we do is we come over here, we make sure amps are selected, and then we come over here and put the meter in line, or what we call series, with the load. Now, an ammeter has almost 0 ohms worth of resistance. So you never, ever, 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 ever put the ammeter in parallel with anything. Never put it across. Everybody understand that? Luckily, they fuse those, but sometimes the fusing of the meter would still be high enough to damage the circuit that you're trying to measure current. So we had a device. It was a transmitter for an overhead for a crane, and it had a fuse in it. And if you tried to measure with an ohm meter, it blew a fuse. So that was a situation. It took us a little while to figure that out, by the way. So we blew a lot of fuses. So we had to figure out another way to check if the fuse was good or bad. So ammeters, voltmeters, and ohm meters. So voltmeters do what? How do we connect those? Across with power on. Now, depending on, you need to know the procedures or what's going on at your company. A lot of places, when you get into extremely high voltages, they want you to turn the power off before you can connect a voltmeter. So you turn the power off, connect the meter, and then turn the power on. When you get ready to disconnect it, what's the safest way to do it? Turn it off, disconnect it, and then turn it back on. On meters, you're always going to so you make your measurements with power on. What do you do with your ohm meter? This is a cross, but you always use an ohm meter with what? Power off. And then ammeter, you have to connect it in series or in line with what you want to measure. Are we okay? Okay, so now we know the difference between an open and a short. In cable splicing and installation, you're either going to create opens or shorts by incorrect termination or incorrect splicing, or putting too much stress on the cable. The name of this course is Installation, Cable Splicing and Installation. They left off the termination, but we got to teach that too. Installation, a lot of times we pull these conductors through tubes we call conduit, which we'll talk about later on. And if you don't pull them right, what could you do? You could stress the conductors and break them. I've seen people break conductors all the time trying to pull them. Direct current flow in one direction. The electrons in the DC circuit flow from electrons flow from the negative terminal of the voltage source through the circuit back into the positive terminal of the voltage. Voltage source never changes polarity. And the big advantage of DC is we can electronically control it. AC is hard to electronically control. Y'all understand that? So your cell phone runs off of DC. Electronic devices are going to run off of DC, direct current. So DC generators create voltages magnetically. Batteries create a difference if the DC voltage chemically. Thermocouples create a voltage from heat, a difference in potential. Solar cells, of course, produce a DC voltage from light. Piezoelectric devices create a DC voltage from force. Electronically, we have what we call them power supplies, and electronically we can convert AC to DC, which thank goodness. So my computer runs off of DC, but Alabama Power don't generate DC. What do they generate? AC. So what do I have? This guy right here. What's this guy right here doing for us? So here's Alabama Power. Yeah, this guy right here is converting AC to the DC required for my computer. So if I took this thing out and jumped this thing directly into that, it would blow my computer up. Because this computer's not designed to run off AC, right? Everybody okay? So here's some pictures. Batteries, everybody's okay with that. Cells, they're actually technically cells. So batteries mean more than one, right? So if I was going into an artillery battery, that means there's more than one piece of artillery in there. So when we use the term battery, it means more than one. More than one. So these are the guys that people call batteries. These are actually cells. But as soon as I connect two of them together, I've created a battery, right? You understand that? So in the old days, they called them cells, but people saw these and we call them what? Batteries. They both mean DC, and people didn't understand the difference between a cell and a true battery. So why did we start calling these things? Yeah, batteries. But they're not really batteries. Now, 9-volt is a battery. So if you take a little 9-volt and you strip it apart, you'll see 6 little cells in there. So a 9-volt battery is a battery. These guys here are built in them. They have 6 cells in there. So that's why you got 6 caps on top when you put water into each cell, right? If you know that. And there's 6 cells in here. Each of them makes 2 volts per cell, so that gives us 12 volts, right? DC generators. You might run into these when you're out at a plant. Most of the time now, we don't use many DC generators because DC generators are very, very expensive per watt, per kilowatt. So normally what we do if we need DC, we use an AC generator and then we convert it to electronics and convert it to DC. And that's what they're doing in your car. So in car, you have what they call an alternator. What type of current do you think an alternator creates? AC. If you put AC on your on your radio, it'd blow it up. So what do? Well, they electronically convert the what? The AC to DC. And it's usually inside the alternator. They call it a rectifier center. Y'all see these guys? These are solar cells. These create DC from light. Piezoelectric, if you smoke cigarettes or got a cigarette lighter that does that little click, that's piezoelectric. So piezoelectric creates DC from a force. So that's what's happening when that thing snaps. It's snapping a little hitting up against a little piezoelectric crystal and generating a voltage high enough to cause an arc to light your cigarette lighter. And then thermocouples. Thermocouples are really, really neat. They create a difference of electrical potential, DC, but they do it proportional to heat. So we use these guys right here to precisely measure heat. So your oven's got a thermocouple in it. If you got a gas water heater, it's got a thermocouple in it. AC, alternating current, constantly swaps directions. The voltage source in an AC circuit constantly swaps polarity, which causes the current to do what? The big advantage of AC, it's less expensive to generate. It's extremely efficient to transmit. Voltage levels can be easily changed by devices called transformers. And AC motors are a lot less expensive than DC motors. Now the problem they were having is when we originally decided to transmit power electrically, and we had a guy that everybody probably knows called Thomas Edison. Thomas Edison was a big DC man. So he envisioned sending power using direct current. So they came up with what they call dynamos or DC generators. So Thomas Edison had these DC generators. And then we tried to transmit this power, but we're trying to transmit this power over distance. So we'll draw this guy right here. Now the problem is if I try to transmit a lot of power over distance, what are we going to become very concerned with? Resistance of the wiring. And we looked at a national wire gauge, right? You'll understand that. And even a 4-aught wire has a certain amount of resistance. So what was happening when they was trying to transmit this, they would have all this line loss. So what they did is that limited the distance that they could travel to about 1 mile. After 1 mile, they would come over here, they would have another generator, and then it would transmit power over the lines for about another mile. And then they'd come over here and they'd have another generator, and then this would have a transmit for another. So what they had to do is they had to split the whole power grid up into very short blocks because of the opposition of the conductor. That makes sense? They couldn't run conductors this big. So that means you would live next to a power station, because everybody would be within a mile of a power station. If you wasn't within the mile, they couldn't get the power to your house without the lines dropping all the voltage. So this is what Thomas Edison was doing. I forgot the city. I think it was New York, and they had power lines and generators all over the place. There was a guy called Tesla, which is the father of alternating current. Figured out another way we could do it. What we're trying to do is we're trying to transmit power. And power is equal to what? What's the main formula? You have V times I. Well, if I try to solve for the amount of power, so power, if I transpose the formula, is going to be equal to P over V. So that means if I'm trying to do 1,000 watts of power, and I'm trying to do it at 1 volt, that would take 1,000 amps of current. If I'm trying to do it at 2 volts, that would be 500 amps of current, right? You understand? If I'm trying to do it at 100 volts, that would be 10 amps of current. If I do it at 1,000 volts, that's 1 amp of current. If I do it at 2,000 volts, that's 0.5 amps of current, right? So the higher we make the voltage, what goes down? Current. Now, what's the problem with high voltage? Huh? What's the problem with high voltage? So I is equal to V over R. So the amount of current we have flow through something is directly proportional to the voltage. So my body has resistance. The higher the voltage I get into, the more likelihood it is for me to get killed. Y'all understand that? So the advantage of high voltage is that I can send more power with less current, but it becomes very dangerous for humans. The advantage of low voltage is it's safer. Y'all understand that? So if I come over here and use an AC generator, so what I'm going to do is we're going to change this symbol over. I think I showed y'all the symbol for an AC generator. So what I'm going to do is I'm going to come back here, and here's an AC generator. And the first thing I'm going to do is I'm going to run it through what we call a transformer, and I'm going to step it up. So let's say over here I'm generating 100 volts. Over here I'm generating, I stepped it up to 10,000 volts. And now before I use it, so what we can do with a transformer is we can do what? Is we can step the voltage up for transmission. Over here we can step the voltage down for safety. Okay, so let's say I come over here and I turn on a 100-watt light bulb. And we'll make it very simple. We'll say this is 100 volts. Well, over here, when I turn on that light bulb, I'm going to say, okay, that's 100 watts, 100 volts. I is equal to P over V. So that's going to be, I would be equal to 100 over 100. So I is going to be equal to 1 amp. You understand that? Now over here, now transformers do not change power because power is work. So I can't change power just because the voltage goes up. But over here, right, I would be equal to P. What's P? 100 watts divided by 1,000 volts. So what would be my I right here? It's going to be 100 milliamps, or 0.1 amp. No, it's going to be less than that, ain't it? It's going to be, yeah, it's going to be 0.001 amp. Y'all understand that? Right? Makes sense. So in a transformer, and then I get back over here, this guy here's we're going to be back at 1 amp over here. So what I can do with AC that I can't do with DC is I can step it up for transmission and I can step it down for safety. So what does everybody have right by their house? I mean, in Alabama, most of them's up on power poles. If you live in a newer community, it's probably buried in the ground, but you've got a transformer at your house, right? These big old round things that's on the house. On the other side is probably 2,300, 2,000, 3,000 volts that if you got into, you would be dead. And then they step it down for your house. We get 2 voltages at our house. What's the 2 voltages used at, or what MC calls the 2 voltages? What are they are? We have 240 and we have 120. Now, why do we need 2 voltages? So these guys right here run all your high power loads. So your dryer, if you got a clothes dryer, it's running off 240. If you got a big old HVA system, it's running off 240. But all these power plugs they're not plugged. If they're plugged in, the plug is usually behind the appliance, right? Down at the floor. So how do you unplug those things? You have to actually pull those big old stoves out or pull your big dryer out to get to that plug. They put them down there on purpose. If you got HVA systems, they're hardwired. If you got electric water heater, they're hardwired. They don't have switches on them. What do we use 120 volts for? Well, all these outlets right here are what? 120 volts. 120 volts is a heck of a lot safer than what? 240. So what do we use high voltage for? Well, we use high voltage, but if you want to work for U.S. Steel, they have 6,000 volts available at that plant to run, because they've got some 3,000-4,000 horsepower motors. If I was going to try to run that on 240, the thickness of the cable would probably be as high as this roof right here. But if they run it at 6,000 volts, then they can use smaller conductors. So that means in this line right here, over here my conductors would have to be bigger. But over here, what can I do to these conductors? I can make them a lot smaller. Instead of using copper, I can use what? Aluminum. What advantage does aluminum have over copper? A lot cheaper. And then also it's a lot lighter. So not only am I saving money on my conductors, I'm saving money on the towers that support that conductor. Because copper is pretty dang heavy, right? You understand? Aluminum is real light. So I'm saving a ton of money, but the problem is I don't want to use, down here I'm going to shift back to what? Down here we'll shift back to copper. Because now we're going to try to get it closer to ground. The voltages are lower, so that means we can use copper. That makes sense? So that's the advantage of AC right there. That's why Alabama Power thank goodness for AC. If AC was never discovered, then that means we would be living next door to a power station. And there'd be cables all over the place. Right? You understand that? But now we don't have to do that. So where does, some of y'all might know this, where does Lawson State get its power from? Tennessee. Bessemer's on TVA, Tennessee Valley Authority. All their power plants are up around the Tennessee River. Well, how in the world can they get that power down here? How can they get that power down to Bessemer? Somebody tell me. How can they get that power down to Bessemer, Alabama? High voltages. I mean, we're talking about high voltages. They get that sucker up to almost, some of the transmission lines are almost 800,000 volts. 800,000 volts, they could send 800,000 watts of power with 1 amp. Y'all understand that? 1 amp. They could send 1.6 gigawatts worth of power with what? 2 amps. So, you know, so that's, but if I got into 800, if I got close to 800,000 volts and ground, it would come out and meet me halfway. Not even halfway. I think 11,000 volts, an arc an inch or something like that. It might be 5,000, well, arc an inch. And we're talking about 800,000 volts. So where are these transmission lines at? Are they close to the ground or are they real off the ground? Way up there. And they're really spread apart. You see those real high tension lines, those arms that carry those cables, they're really far apart. So the advantage of AC, of course, is we can transmit it. I can get it to my house from Tennessee. Of course, my house is on Alabama Power. But if you live in the city of Bessemer, if you pay your power bill down there on, what is it, First Avenue, you're on TVA. And your power is coming from up around the Tennessee River, right? You understand that? And how they did, I think it was a big deal with U.S. Steel. U.S. Steel came into Bessemer. You know, Bessemer was originally developed from a steel town. They actually had a steel mill in downtown Bessemer. You can still see some of the remains. I forgot where it's at over there. Whatever street that is that runs out to where the old Pullman used to be. It's on the right. All that out there used to be Bessemer. And it was named from the Bessemer, what do they call that? Before they came out with the open hearth furnaces where they actually make the metal. They called it a Bessemer blast furnace. And that's how Bessemer got its name. And I think they cut a deal with TVA to run the power down through here because it was so much cheaper from what I understand. So that's why Bessemer ended up on TVA. And everybody around us is on Alabama Power. I think that's the story. So AC this is alternating current. So DC will not pass through transformer. AC will. But what the transformer does is it don't change the power, but it changes the voltage. Right? It changes the power a little bit, but for our practical purposes, we'll assume the transformers aren't 100% efficient. We can generate power with AC generators. We can generate AC from electronics. And by the way, on DC, we forgot the last one, which is what? Bioelectric. Do you know anything that's bioelectric? Yeah, we're bioelectric. So we create electricity. What was the metrics? You know what that all the machines was using humans for? In the metrics. Oh, I've seen the metrics, right? You haven't seen the metrics? The metrics, all the machines have taken over the world, and all the humans are hiding underground, and they're using us for they put us in these little incubators and hook up cables to us and using us as batteries, and they put us in a trance, so you actually think you're living in this real world that we're in. So right now you're not even here; you're in a battery, you're in a tube somewhere. generating power for all the machines that's running the world. So y'all ought to watch the metrics. It's probably on Netflix if you got that. So we're bioelectric. So all our impulses, all our nerves create electricity. This is what travels over our neurons up to our brain, and that's what your brain does. It processes electricity. So we're bioelectric. Lightning bugs are bioelectric. Electric eels are bioelectric. What's nice about electric eels is they create both DC and AC. So they have a real low charge that they can discharge if they're trying to stun something, and they have an extremely high AC charge that they can generate if they're trying to kill. I forgot the voltages. It might be on the slide. Electronically means I come in and I bring in so this guy right here is called a function generator. That's this guy right here. And what it does is it plugs into Alabama Power. And then what it does is we can electronically generate AC. So what we do is we take AC, we convert it to DC, and then when I convert it to DC, I can electronically control it and turn around and recreate AC. So I needed to hook up. An oscilloscope is a device where we can actually see exactly what's there. So this is what Alabama Power looks like. So this is the 0 volt reference right here. So up here, this would be a positive voltage, and then it drops down to 0 again, and then it goes what? Then it goes negative. So what's happening in an AC circuit is the polarity is constantly swapping, and the electrons are moving back and forth, 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 back and forth. And but this back and forth action is what makes the transformer work. So this is what makes AC go through the transformer. DC So this is DC right here. So here's 0 volts. I can't get it down to 0. What I'm going to do is change the level. Where that came from. So this is DC. So what I'm doing is I'm changing the level, and what do you notice? It never goes below this line right here. So that means DC never does what? Changes direction. But I can take this DC, and the advantage of DC is that we can electronically control DC, and I can use that to convert it back into AC. Thank goodness. Because sound is AC. So if I was to look at audio, which I could, audio is AC. So, but I don't have, my car is not AC. My car runs off of what? DC. So what is your radio doing? Your radio is taking DC and electronically converting it into what? AC to represent that sound. If you put DC on a speaker will burn up. So a speaker has got to have AC. And we'll might not find out why, but if you take AC, you'll definitely know that. So what we can do with DC is we can use it to electronically produce what? AC. And that's what this guy is here. It's called a function generator. So if I was to take this oscilloscope and hook it up to Alabama Power, we would see this guy right here. This waveform. Come on. What I'm doing is synchronizing the scope. As I said. called a sine wave, by the way. When you take AC, you'll understand why. So this is what Alabama Power generates right here. Exactly. I would see almost the same thing, but it would be at a real higher voltage, a lot higher. Now, this is very small, but this is being electronically generated. So notice if it's electronically generated, I can change its amplitude, and then I can also change the rate. And we don't do that with Alabama Power. Alabama Power, you can't change the amplitude, and you can't change the rate unless you go through a wall. You can change the amplitude with a transformer, but you can't change the rate. Okay, guys, y'all take a break. 10 minutes. Need to figure out how to get mine. There it is. So AC generators, alternators, y'all familiar with those? That's out there on your car, it generates AC. And then we have a unit in there they call it a rectifier if you ever look at the parts, which is taking the AC and converting it to DC. Mobile DC generators. When we had the big snowstorm of '93, we lost our power for quite a while, so I went out and bought these, and I've never had to use it. Sitting out of my shed. Generators in power plants. This don't look like quite generators. Most of the generators in the power plants are mounted vertical. Some of y'all might have these guys, these DC to AC inverters that you can buy for your car, so you can hook it up to your battery or whatever and get AC out of it. My wife's van's got one built into it. It's actually got a 120 volt outlet in the van that she can turn off and on. So that inverter is built into her system. And then, of course, the function generator, which is what we have when we study AC. We use this to generate not only can we generate different rates of the AC, we can also generate different levels to see how things respond to the different rates. And I didn't put a electric eel up there, which is a very interesting creature. Alternating current provides a voltage and a source that changes direction constantly, right? The repetition produces a voltage waveform that we'll see on the next slide. The AC waveform is referred to as a sine wave because it varies with the trigonometric sign of the voltage and current and power, and that's why it's got the name. Now, when you take AC, we'll look at this and understand, but that's how it got its name. And it's a very symmetrical waveform. It's not linear, but it's very symmetrical. So what we would do if I was to take this positive voltage spike here and flip it around, it would exactly lay on top of the negative. It varies at a certain, and it's not a linear waveform, so it varies, it slopes different as it moves up. Then it hits what we call a peak, and then it drops down and hits a negative peak, and then it repeats over and 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 over. As long as these lights are turned on, that's what the lights are seeing. As long as Alabama Power don't fail, this is what your house is seeing. This thing right here. It's called a sine wave. Sine wave is two different words, by the way, but I always put them together. Now, some things we need to understand, first of all, is what we call a cycle. So this thing moves in cycles, and a cycle is a repetition, right? You understand? So we have 3 seasons in a cycle. Our time is in cycles. We have 24 hours in the day. Once we hit the 24 hours, we start a new cycle, right? You understand that? So one cycle is the repetition of a sine wave. And it's also called 360 electrical degrees, which makes sine waves were originally generated on a circle. And so one revolution past two poles would generate the sine wave. And so it became known as electrical degrees. This will become very important. We'll talk about phase shifts. We need to understand, if we say it's 90 degrees out of phase, that means it's actually occurring here when it should be where? Here. We'll need to understand that just a little bit in conductors, what's going on. An alternation is each half of the sine wave. So we call this guy here the positive alternation. We call this the negative alternation. A frequency is the rate of the sine waves. So Alabama Power generates 60 cycles per second. Oops. Why ain't it selected? 60 cycles for every second. This is Alabama Power. And that's just as accurate as you could possibly do. In fact, some digital clocks that you plug into the wall outlet are timed off Alabama Power. That 60 cycle is so accurate. So like my stove. At home, if my stove turns off, it loses the time. And usually when it loses the time, when it's turned off, then it's timing off this 60 cycle. This guy is extremely accurate. Now, just about any science, people who are fundamental in developing the science get the honor of their name be given, like Volt is named after Volta. I don't remember his first name. So voltage, amperage, ohms, these are all named after people that were fundamental in the development of the trade. So we have a term called Hertz, which stands for cycles per second. So most people say Alabama Power generates 60 hertz. And you abbreviate hertz with an uppercase H and lowercase z. So Alabama Power generates 60 hertz. So it means that dang thing is changing one cycle every 1/60th of a second, right? I mean, I'm sorry, it's 1/60th of a second is a cycle, which is only 16.67 milliseconds. If you don't understand engineer notation yet, it's that many. That's how long a cycle takes. An alternation would take 8.333 milliseconds. So that alternation is up there. AC has no polarity. So DC, we have two polarities. I would come over here and this would be the positive polarity, that would be the negative polarity, and the polarity never changes. AC has no polarity. Considered to have no polarity because the polarity is constantly doing what? Changing. If I've got a DC voltmeter, I'll come over here to make it measure positive. I need to put the red lead right there, and I need to put the black lead right there. AC, it makes no difference. I've seen people try to argue with you. You're supposed to put that black lead on neutral. That's not true. AC has no polarity. Your meter will measure exactly the same thing. AC, whether you put the black lead on the hot lead or the red lead on the hot lead, don't make any difference because AC has no polarity, right? You understand that? Because why? If one alternation is only 8.3 milliseconds or 0.0083, how long is it at any one point on that line? How long is it at peak? You know, it's at peak. We can't even understand the amount of time it sits at peak. So, and of course, the big advantage of this, and we can generate AC. So this is what we call single phase. Everybody okay on frequency? The time is what we call the period. And of course, as frequency goes up, the time per cycle goes down. Right? You understand that? And the formula for period, and you don't have to, or it's not P, it's actually T for time. That stands for period, is 1 over the frequency. So if frequency goes up, the time does what? Goes down, and vice versa. Like I said, this is not a formula. In AC, you'd have to know that or memorize that formula. We don't need it here. But we do need to understand what frequency is. Frequency is the rate of the cycles. And unfortunately, the frequency is what determines reactance. So this thing called reactance, this varies with frequency. And then, of course, resistance does not vary with frequency. So that's the big difference between those two. Does not vary. And I don't know where that popped up at. Where'd that come from? It's not on my screen. Oh, I know it. I know where. I put my arm on the remote for the display. We have what we call single phase, which is what your house gets. Your house gets single phase power. But normally when we transmit the power over long distances, we use something called three phase. So there's, it's going the wrong way. And this is what three phase looks like. So what we have is we have at least three conductors. So if you look on a transmission line, here's 1, 2, 3. Now what they're doing is they're splitting it up between several conductors, usually 3, and you'll see it in a V, in a triangle shape. And what they're doing is that these guys are handling so much power, if I send it on one conductor, the conductor would have to be extremely big. It would be almost impossible for me to string it up and put it on a spool. So what they do is they turn around and break it into 3 conductors, and they hook them up together so they handle the current of those 3 conductors. And what's nice here, if one of your conductors break, you might be able to produce less power, but you're still going to be able to deliver power, right? You understand? It might be at a reduced rate. But there's your 3 phase right there. So when they generate this, they're generating the phases, we call it 120 electrical degrees apart. So when this guy here is sitting at 120, so this would be 0 degrees electrical degrees. This right here would be 90 electrical degrees. This would be at 270 electrical degrees. So right here at 220 degrees, when they cross right there at 120 degrees. Now why this is more efficient is because now the power is being spread across 3 conductors instead of being spread across 1. So in 3 phase, if I was to come up here and measure I, and then I measured V, the actual formula that we're sending on the 3 phases is I times V times the square root of 3, which don't mean much to you. But what happens is now is the power is spread across 3 conductors. And then plus another advantage to it is that it automatically creates an electrical field that rotates. So if I come over and put these 3 phases 120 electrical degrees apart, and then I put a big thing in the center, well, when this phase is going down, this phase right here is building up, and what does it do? It causes the phase to shift. What that means is whatever's in here is going to rotate. So what that means is, right off the bat, 3-phase motors, we don't have to do anything special to them to cause the motors to run. Because the outside field is doing what? It's automatically spinning between those phases. Those 3-phase motors are a heck of a lot more efficient. 3-phase is more efficient because I get the square root of 3, but that means I've got to run 3 wires, at least 3 wires everywhere. So this is why your house, the power demand at your house is nothing compared to the power demand at US Steel. So these big high power demands, they're going to use 3-phase. These low power demands, they're going to use single phase because it's so much easier to run. But what we have to do on your motors on single phase is we have to create a rotating field. And so we use these things called capacitors or inductors have to be on a single phase motor. And we'll look at that. And what they do is they create the phase shift by themselves. So your house gets single phase. That single phase there, that single phase here. We have 3-phase here, but I don't think we've got any running down here. The motor control slab, you'll have 3-phase available. And if you do commercial wiring, you'll play around with 3-phase a little bit. We have 3-phase at the campus. So, because the campus has a real high power demand, but when it gets down to me, we go back to single phase, right? So what's the advantage of single phase? It's a heck of a lot cheaper or efficient to transmit. So that's why your transmitted power is 3-phase. The problem is it's very expensive because it takes at least 3 conductors. Single phase takes how many? 2. And you think about that, don't seem like much, but when you think about where your power comes from, where's the nearest substation to your house? You don't live next to a substation, do you? So that means if they ran 3-phase to your house, it would make your motors a little cheaper, but we don't need 200 horsepower motors in our house. Every motor you got in your house is a fractional horsepower, like a quarter horse or a third of a horsepower. So they're very small, so they don't need the extra efficiency that we would get from a 3-phase. So if I try to run a 3-phase motor, a single-phase motor on 300 horsepower single-phase motor, just getting that right there makes a lot of difference, right? At times the square root of 3. And there's our power formula. So our power formulas change a little bit if I'm using 3-phase. So my power formula is what I would do is I would take all these and do what? Just multiply by the square root of 3. When current flows through resistance, a conductor, of course, when we put current through resistance of a conductor, what happens? We get a voltage drop. The higher the voltage pushing the current, the less current is required to provide required power. We've already looked at that. Transformers can do what to the voltage? Yeah, they can step that voltage up for transmission and do what? Step it down for safety. The power don't change. So if we step it up, it requires less current to produce that, send that power. And this is what I tell everybody, you don't pay your current bill every month. You don't pay your voltage bill every month. You pay your what? Power bill. So you're paying for work. You're paying for watts. You're not paying for I. So the higher we can get that voltage, the less current's required. I'll ask people what's the advantage of 240 volts, and a lot of people say it's more efficient. It is not more efficient. It's delivering power. It's just that it's delivering power. It's delivering that power at a lower current, which means now I can use smaller conductors to get that power out to my air conditioner. I can use smaller conductors. So instead of using 6-gauge wire to run my water heater, right? You understand? I might use 10-gauge wire to run my water heater. So remember, the bigger the number, the smaller the wire, right? And so now I can pull that stuff through my wall instead of running it through my ceiling. So the only advantage you get from high voltage is it's cheaper to install. And it allows us to use smaller what? Conductors. So is 240 volts more efficient? No, because it's delivering power. So all your high wattage loads run off of 240. Your low wattage loads run off of 120. That makes sense? Use smaller circuit breakers. So now I can use a standard circuit breaker. I can use a 50 amp breaker on my water heater instead of a 200 amp water breaker, which I don't even know you can get. These are 3-phase transformers. So anytime you see transformers in groups of 3s like this, that means you're dealing with what? 3-phase. Sometimes they use individual single-phase transformers that are wired for 3-phase, so each one of them get a different phase. Sometimes a 3-phase transformer is built in. This causes more to install, but it's cheaper to maintain. So if one of these guys go out, I got to replace the 3-phase transformer. If one of these guys go out, I replace one single-phase transformer. So Alabama Power usually uses this method right here. But if I was to go down to like, I think Chick-fil-A down there, they have one of these guys because it doesn't occupy as near as much space. So the advantage of this is it's cheaper the first time around. These guys right here is cheaper to maintain. Does that make sense? Yes or no? Of course, everybody's seen these. What do we call these? Yeah, we call them substations. What do the substations do? Huh? Well, what do they do? What's the function of a substation? Nobody knows what we got any big old substations out there for. Nobody in this class knows that. What's the function of the substation? What are they made up of? Well, mainly they're made up of transformers. So what do substations do? Well, it steps the voltage up for transmission, or it steps the voltage down for what? Safety. That's all they're in there for. All they are is just transformers. And these are the ones that step it down from extremely high voltage. You can tell that by what these big old bus bars are running, how far they're apart. But we transmit them over here. This over here might be 75,000 volts. Over here, this might be 2,300 volts. I send the 2,300 volts out on power lines in my house, and then my house has a transformer out there, which steps it down to 240 or 120 for my use, right? You understand? The only function of those substations are to take that high voltage and step it down to a low voltage for safety, a lower voltage. It's not really low. It's still pretty high. And what determines that low voltage side, of course, is how far that power's got to go, right? You understand? So what determines those high tension lines is how far that power's got to go. So they got interstate, they got intrastate, they have local service, they have different service substations that they build depending on how far the secondary side or the low side has got to send that power. And then I do what? Then when it gets to my house, I have my transformer. I have a single phase transformer that steps it down to the voltages needed for my house. And we have two voltages over here. 240 is for high wattage loads. 120 volts is for low wattage volts. 120 we got access to. There it is on the wall right there. Now 120 volts is above what the National Fire Protection Agency considers to be a lethal voltage. Anybody know what the lethal voltage is? Something you should know. Anything above 50 volts is considered to be lethal, which means it's the potential to kill, right? It's just like if you get bit by a snake, it don't mean you're going to die, but you have a potential for dying. 120 volts is above that. But 120 volts, if it's going to kill you, you're going to have to be in a special situation, like working in Alabama outside in the summertime when the humidity is about 50% and you're sweating, right? You're real susceptible. Or if you have cuts and abrasions on your fingers and you get into it, you could probably get killed by 120. 240 is twice as likely to kill you. So we're working with lethal voltages, even in houses. So you need to be careful with it. But odds are, like I said, if you get shocked by 120, it's highly unlikely it will kill you. But it has the what? It has the potential. So this is a typical transmission system right here. I'm only using 275,000 volts. The highest that I've heard of is around 800,000 volts. So we have a power company. It generates voltage. It's pretty high to reduce the size of the conductors. Then it'll run through a substation that's going to do what? Step it up. Then we step at the extremely high voltage to come over here. Then we run for another substation somewhere that does what? Step it down. And it might not step it down all the way to your house. It might go through two substations before it gets to you. So we might transmit at 275,000 volts, but US Steel needs 6,000 volts. So they'll take that 275,000 volts instead. They'll have 6,000 volts, and I think they got 6,000. They have 440. They have I'm not sure, 440. They have 240, and they still have 120 because they have people that live out there, right? They don't live, but they've got wall outlets out there. And then they might take that 6,000 volts, and they might run it to another substation and step it down to 2,300 for residential use. So how many substations it goes through to step it down depends. And I might decide, I might get over here and need to send it further, so I might run it to a substation that steps it back up to what? 20,000 volts to send it out to Joe Blow's farm out there somewhere. So we run through multiple substations. By the way, the input side of the transformer bank, we call this the primary. The side that's pointing toward the load, we call these secondaries. So this would be the primary of these transformers. This would be the secondary. This would be the primary of these transformers. This would be the secondary. The primary of this transformer would be here, and the secondary is what's feeding your house. So the secondaries always point toward the loads, and the primary always points toward the source. You know, that's what we were looking at. So here I think we're turning on over here we're turning on we need 1,000 watts at 120 volts. It's going to require what? 8.3 amps. Okay, at my house. Over here though, we stepped that up to 2,300 volts. So at 2,300 volts, it would only be requiring what? 450 milliamps or 0.45 amps. Then over here on the 2,300 volt side, if we're doing our 275 kilovolt side, we're only dealing with 0.0036 amps. So now I can start doing what? Instead of using copper, we can jump back to what? Aluminum. Right? Does that make sense? Huh? In the middle. Usually right in here, we start going to copper. Wait a minute. Because of this. V is equal to I times R. Aluminum's down as the fourth best conductor. Copper as at the second best conductor. Now aluminum is in the low current side. Okay. So if your voltage is extremely high, likelihood they're going to use aluminum because the highest voltage is high. And of course, I is equal to P over V. So the higher I make the V to transmit that power, so we're trying to transmit power. So the higher the V is, the less the what I is. So now I can use a conductor that's got more resistance to it. Because how much voltage we got drop is I is equal, what V is equal to I times R. So if I've got a certain conductor like aluminum, then R is going to be bigger. But if I get the current low enough, the voltage drop over that wire is not going to be enough to affect it. That makes sense? So what it does is on these we call them high tension lines. These are the lines that have extremely high voltage on them. Them suckers, you can actually feel you can hear the magnetic field on those lines. You can hear them what? You can hear them hum. You can hear that thing changing states. It's generating an electrostatic field that moves through the air. That's what you're listening to. Well, the transformers hum too, because you're changing directions, and those wires are moving inside there. So that's why transformers hum at you. And the more current you put through them, the more they do hum. You ever been on these big old high tension lines, and you can hear them humming at you, because that's what's happening. It's generating those electrostatic fields up there. And what advantage does aluminum have over copper? Yeah, there's no telling how much the power grid would cost if they had to run copper all the way from the power plant. But they don't. They use what? Aluminum. And aluminum has two advantages. Not only is the metal cheaper, but also it's a lot lighter. So that means these big old towers that support that aluminum, if that was copper, they would have to be what? I mean, they would have to really be beefed up a lot, right? So that's what we do. That's the advantage of AC over DC. We can step it up for transmission, so now we can send it over great distances without a lot of voltage drop. We can't do that with DC, because DC we can't do what? We can't step it up and step it down. We can't step it up for transmission and step it down for use. So we transmit power in AC. Power is transmitted in AC. I don't know of anybody that uses DC. That makes sense? The instantaneous voltage of an AC sine wave is constantly changing. The DC average, and this is what gets a lot of people hurt. I'm going to pause this. I'm going to find this wall out. Let me show you this.